Okay, I'm wanting to move on to the network strand of applied mathematics. It's reasonably straightforward. You're going to learn about various sort of processes that you go through when you're given a set of information. You can represent it in a graphical format, which is what we're going to primarily concentrate on today. You can show something in a sort of numerical format, which is when we get on to things to do with matrices. In certain circumstances, and be able to look at a variety of different problems. And I'll try and talk about those different types of problems that you might come across. Not all of them, but just give you a flavour or an introduction to the topic. So a graph, the idea of a network or a graph, okay, is here's a visual representation of four things that have been connected up. So the four blue dots, okay, we call them vertices. So each one is a vertex, vertices is plural, or you can also call it a node. Okay, and then there are lines that connect them up, and we usually call those edges. Okay, but lines is fine as well. But I'll commonly call them edges. You'll note very quickly, please, that there are lines that go diagonally across from top left to bottom right, and likewise from top right to bottom left. And there is a point here where those lines cross. This is not a node, okay? This is not an intersection, okay? They just happen. You can imagine they're bridges bridges and tunnels over each other. There's no way of going along this edge and then suddenly turning towards that node there. Okay, so the idea is you can go from this node all the way across. Okay, that's no problems. You can go between those two nodes, but that road doesn't do anything else. So so we can have these nodes. They're clearly defined, or vertices. Each vertex clearly defined, and the edges we understand. Where those edges go to. So and you can use a graph for any representation of anything that is interconnected. So roads is a classic one, social media contacts, and then you can look at other resources. So, electricity, communications, all those things, how they might be connected. If you're there looking at how to connect up several different townlands to a communication network, be it Wi-Fi or telephone, and you can represent those different townships with a node, and how you try and connect them up with your cabling and so forth, or other methods of connecting data. You can represent those using edges. So there's a lot of terminology that we need to get our head around and be aware of before we can really sort of get stuck in with doing lots of problems. So, so the first we've met is vertex and edge. So if we have a vertex which has an edge coming out of it, but it literally, as the name sounds, loops around and comes straight back. So, i.e., the start and end of the edge is the same vertex, then we refer to that being a loop. Okay, so the edge connects a vertex to itself. And you can see that there, this vertex has got two edges effectively coming out of it. Okay, one loops around, and the other one is just another edge going in another direction. You can have two nodes that are connected by several edges. Now, what I would say to you is you've got two very closely drawn lines. It tends to be the case if they're drawn as more of an arc. So it might be an arc above and an arc below as such, okay, rather than being so close together, because that's not particularly clear. So usually you would have one edge above, one edge below. So there's two examples there. You've got first one is where you've got two vertices that are just connected by two edges. So that's multiple edges. Here you've got a slightly more complicated example of a network. Okay. So you can have loops and multiple edges, and we need to be aware of that for definition purposes later on. So a simple graph, okay, is one that has no loops or multiple edges. So it's simple, it's straightforward. You're cutting out the noise and the unnecessary bits. You're just dealing with how nodes are connected with each other. Okay. Each pair of vertices is connected by at most one edge, i.e. there's no multiple edges. We can have a weighted graph. So again, we'll show you examples later on, but let's say for sake of argument, if you're connecting some things together, say be it towns, you might find that two towns are 7 kilometers apart, and another two towns are 2 kilometers apart, another pair is 5, another pair is 4, so you can represent the distances between those townlands with this graph, for example, here, where you've got the weight of each edge, i.e. it's a cost or a length. It could be anything. It could be the cost of doing something in terms of money. It could be cost in terms of distance and resources. If you're laying a cable, you need to know the distance. Or it might be in terms of time, how long it takes for something to be connected. So there's various different types of ways in which we want to think about the weighting. But the idea is the edge is labelled with a number to demonstrate the fact that there's a weight or a cost to it. Okay. And I suppose if you wanted to say yourself, right, okay, what's the cheapest way of getting from this top left to the bottom right? Well, you could go one way, which will cost you 11. Or you could go in the other direction, which costs you 7. So we can clearly see that doing the 7 will be a far less costly way of going about that journey. We can have directed graphs, so you have the edges have got an arrow to it, i.e. a direction. You can only go in one direction, and it's the direction of the arrow. This is not rocket science, okay? But you can show that direction if need be. And this sometimes can be used if you're sort of, for example, argument, talk about the relationships. You might have an organizational chart for an organization, and sort of levels of responsibility and so forth. It might be to do with a family, so you can have a grandparent that has then the offspring, children, and then from there it goes on down. So you can show the direction of the relationships using the arrows. We have a graph. It's a graph. A graph is a diagram, a network that shows a series of nodes and edges. And much like sort of set theory, you can have a subset, which is a part of a bigger set. Here you can have a subgraph, which is a part of a larger graph. Okay, not rocket science. Straightforward, hopefully. Now we can look at graphs, and we can draw them. So I could give you a series of instructions of connecting several nodes together, and one person will draw it looking one way, and another person will draw the graph looking at it differently. So you can have a situation where effectively it looks the same, but it may be a subtle difference, or it might look completely different, but actually they're the same. So these two examples here, they are actually very similar. The only difference between the two of them is one's been labeled 1, 2, 3, and 4, the vertices, and the other one has the nodes, vertices labeled A, B, C, D. So they're not identical. Okay, but you can also say that they're, you can say they're isomorphic. Okay, the same structure but different labels and or layout. And here they've got both got different labels, but we've also got a slightly different layout. And actually, the only difference, if you take a moment to look, if you imagine turning the I suppose it looks like it's not quite a burger, but the ABCD diagram, if you turned it 90 degrees clockwise, and if you sort of took C from being inside that the edges that go from A to B, and you've brought it outside, okay, you'll see it's the same as where 3 is outside. I could put 3 inside into the middle of there, and there'll be a line going to 3 towards 1 and towards 2. So if I take C outside over here and have the connections to A and B, then it would effectively have the same layout. So these are not identical, they are isomorphic. They are isomorphic because effectively the relationships of the nodes are the same. Yes, the labels are different. Yes, the positioning of them are slightly different, but the structure of the layout arcs, edges, are the same, basically. So, just a quick summary of what I've gone through so far. I've gone through the idea of a graph, loops. We've got simple graphs, weighted graphs, directed graphs, subgraphs, and then we've got graphs that are maybe isomorphic or identical. So let's sort of talk about an example. Okay, so what we might do is we might I'll give an example in a moment, but just as I said to you beforehand, connections, if you're project managing or if you're wanting, to do with an organization, trying to understand the relationships and connections of people, you're looking at communications, road networks, transport, anything to do with transport. A graph, a network graph, can help you to simplify what is going on and be able to make sort of decisions on whatever task you're working through. So what we'll do is I'll go through an example, and I'm going to try and go through sort of the variety of different types of questions you could get, okay, and which I'm giving you a sort of a little bit of a window into the sorts of tasks that you'll be doing through the next few chapters. So here's a diagram that you should be fairly familiar with. Okay, and that is a map. It shows fairly accurately the relationships of the various different towns and cities and villages that are in Kilkenny. It doesn't list them all, I know. Sorry if your little township or village is not on there. I'm sure there's someone from Bennett's Bridges getting annoyed right now. But anyway, the point is that it's just a picture I've gotten off the internet. Okay, and it shows relationships. Now that, to some extent, it can be slightly complicated. Maybe let's make this a little bit easier on me to explain. Let's take a smaller section of that, okay, and let's sort of now think, well, how might we actually show the relationships that are between these various different towns? So let's assume there are roads. I know it doesn't show there's any roads going to Kells, but let's accept that there are some roads to Kells, and there's more than just the yellow and red lines on the diagram that can get us to these various different places. But let's say there's a network where I'm showing, and let's just concentrate on a certain few. So Kilkenny, Gowran, Kells, Thomastown, Ballyhale, Callan. We're going to ignore Inistioge, too far away. So let's just make this easier. So I've gone from that diagram. I'm able to show the relationships that I want to talk about in this hypothetical scenarios, and I can represent the relationships of those places with that network. Now, actually, the positioning of the nodes do actually represent realistically what is in reality. Now, it doesn't stop me from changing them and moving them around and having them in different places. I could pull Kells outside of that sort of center, sort of quadrilateral. I could do various different things. Okay, so it doesn't really matter about the actual physical positioning of them. You just want a diagram that shows the relationships between. So here we can say that, well, we can go from Kilkenny to Callan or Kells or Thomastown or Gowran. If I want to go to Ballyhale, I can't go directly from Kilkenny to Ballyhale. I have to go via either Callan or Thomastown, or make it more complicated and go via Kells and Callan, or Goran and Thomastown down to Ballyhale. So let's put in some distances. So these are fairly accurate distances of going from Kilkenny to Goran. It's 14 kilometres, and so forth and so forth. So I've now have a weighted diagram. Okay, I'm not going to have any direction because effectively we're assuming that we can go in both directions, Kells to Kilkenny, and likewise Kilkenny to Kells. And what we could do is we could sort of talk about the different types of problems we might have. So we can go through. So I'm just going to take a grab of this picture. I can. Sorry about this. I can't do this one frozen. Okay, so the first one that I've already mentioned, the idea of the shortest distance. Okay, and there's very simple, shortest distance from Kilkenny to Ballyhale. Okay, well, I'm not going to go through the actual algorithms and so forth. We'll just sort of try and see it sort of in a visual sort of way. You can sort of go via Callan. That will take you. That'll take 39. You could go via Thomastown, that's 17 and 9, which is 26. You can go via Kells and Callan. That's going to cost you 26 to go via Kells as opposed to 20. So that's not as good. Again, if you went via Goran, 14 plus 13 is 27. That's more than the 17. So in a sense, the quickest routes would be either 39. Via Callan or 26 via Thomastown, so it doesn't take too long for you to say yourself, well, that's a case of saying we've got shortest distance is Kilkenny. Pen's not working. Kilkenny via Thomastown, Ballyhale, at the cost of 26. Okay, if you look at another problem, let's say you're going from Callan to Goran. Okay, do you go via Kilkenny with a cost of 34? Do you go via Kells? No, we already discussed the fact that going via Kells is more expensive than going direct. But we could go via Ballyhale. It's got a cost of 28. Plus 13, which is going to be 41. So again, we can sort of see that the quickest or the shortest or the least distance, the least costly distance from Callan to Goran is 34. Okay, so those sorts of problems there where you can do it in a systematic way. We'll talk about the processes some other time. But the idea of going from A to B, what's the shortest distance? What's the least cost? Okay, now you can have other ones. You can have problems where actually it's not going from A to B, it's a shortest distance where we have to go to every single node at least once. Okay, we might have a situation where our start and finish isn't important. So let's just say, for sake of it, start at Callan, and let's say to ourselves, well, if we go to Callan to Kells to Kilkenny to Goran to Thomastown to Ballyhale, I've visited all the nodes. Okay, and that is a route that I could take. There are possibly other ones. So I could go Kells to Callan to Ballyhale to Thomastown to Kilkenny to Goran. Okay, now I would argue that that's not as efficient as if I had gone via Thomastown to Goran to Kilkenny. So if we just that's 13 and 14 was cheaper than doing the 17 and 14. Okay, so you just have to sort of be aware. Let's do a different colour for that one. So 17 and 14. So my first example wasn't as efficient. My second one that you can see there now, that's slightly more efficient. And again, there's ways of being able to work out, what is your shortest distance. Now, that was just where I didn't really care where I started, didn't really care where I finished. You might have a situation where you have to start and finish at the same place. So we could have a situation where, okay, let's just define where we're going to start. I don't know. Let's start Kilkenny, and let's see, well, how can we? So we can go to Kells, Callan, Ballyhale, Thomastown, Gowran, and back to Kilkenny, and that costs more than the previous examples because previously, once I got to Ballyhale or Gowran, I didn't really care that I wasn't where I started. Okay, I wasn't back at Kells. So here I've started and finished at the same place. Okay, and this is often called the travelling salesman problem, where you're having to travel and visit every single node at least once. Okay, and get back to your start point. You can have a situation where you've got to visit every node just exactly once. So what I would say to you is this diagram is a fairly simple one, and it's not complicated, and it doesn't create too many problems. There are times when you're doing your sort of trying to visit every single node, that because the way in which so if we added in, let's say if we added in Inistioge over here, right? Okay, there's Inistioge, right? Okay, and we wanted to say, right, we want to travel to every single node at least once. So I'm going to Kilkenny, and I want to be able to go to every single node, or that firstly, okay, exactly once. Okay, immediately now I can't do that. Okay, I'm going back to Kilkenny. Let's try a different way of doing it. Let's go right, Kells, Callan, Ballyhale, Thomastown. Now, if I'm going to go to Inistioge, my problem is I have to go back to Thomastown. So I've gone through Thomastown more than once. Okay, so that's not quite what we call a Hamilton cycle. Again, we'll look at that some other time. Hamilton was well, he's not lauded enough. Arguably, he was an Irish mathematician who did some fantastic discoveries that were quite important in terms of progressing this whole topic, this whole subject, and also its effect that it's had on making connections, internet connectivity, and so forth. Okay, so there's an example where I can go from Kilkenny and back to Kilkenny, and I can visit every single node, including Inistioge. The only problem in this example is because of the way that the network is, I have no option but to visit Thomastown twice, effectively. Okay. I don't think we need Inistioge for a moment. Right, and then you've got another one where it's not the nodes that you have to go through every single one. Okay, it's the arcs that you have to go through every single one. So you notice when we did the previous one, we were going from A to B type scenario, going through every single node. Okay, I when I did my route, noticed that I didn't use this route here with the cost 20, nor this edge here with the cost of 17. They weren't used. They weren't needed. Okay, so that was the traveling salesman. So, but what's called the Chinese postman, okay, is one of the examples, is where you're traveling all the arcs at least once. So again, how do I go about doing that? Well, I suppose if I go Kilkenny, Kells, Callan, Kilkenny, notice I can go back to the same place or get more than once. Now, this is not very efficient, so now I have to travel a second time. Okay, in order to be so there, I've been able to draw without lifting my pen. Effectively, I've been able to go around and travel every single road. Okay, so if you think of roads, the road's got houses upon, and the postman goes into each house, so he needs to go along each road. So, but he had to travel she did the journey from Callan to Kilkenny twice. And the other thing is, I didn't end up where I started. So I started Kilkenny, I ended up in Thomastown with that example, I think. So again, how can you go about being able to travel all the arcs at least once? And there is another scenario where you're traveling all the arcs exactly once. Okay, so we did all the nodes at least once, then all the nodes exactly once. Then we have traveling all the arcs at least once, and finally traveling all the arcs exactly once. And I'm going to come back to that scenario in a moment. Okay, we'll park that one. We'll park traveling all arcs exactly once. I'll come back to that in a second. Just want to talk about minimum spanning trees. So if we think about, let's just get rid of the annotations there, hang on. So let's try and just connect these towns as cheaply as possible. Now, I just want to get them connected. So let's say I had a telephone line or internet sort of cables. It doesn't really matter how I get my message from Ballyhale to Callan. It moves in milliseconds. Okay, so if it happens to go via Goran and Kilkenny, so be it. Okay, so it's about trying to pick, in a sense, well, again, we'll talk about trees in a moment. This idea of a network or a subgraph of that network where we're only connecting as little as possible in terms of the arc edges, but we're getting all of the nodes connected. So I could, for example, connect up Thomastown and Ballyhale and Goran and Kilkenny and Kells and Callan, right? Okay, and I have connected them up with a cost of 40, 50, 62, I think it is. Okay, and that's probably the minimum cost that I can possibly create where I've connected all 6 towns with an edge. Okay, and this is, as I said, this is called a minimum spanning tree. And again, we'll look at that. There's a couple of different algorithms we can use to work through that as a problem. So I've gone through quite a lot there. Let's go back, if I don't mind, to so there's a list of all of everything I've spoken to you about. I'm going to talk a little bit more now about trees, along with a few other bits of terminology. So, and some of what I will be talking about here, I have been not using the vocabulary, but you can get a sense of their application. So, again, it's a bit of terminology. We can have a walk. Okay, so a walk is just basically a journey along edges, visiting or going through vertices, okay, or nodes. Okay, so a walk is a sequence of vertices and edges where each edge connects its preceding and following vertices. Okay, we might have to repeat as a situation. We can have a situation where we can go through roads more than once or go through nodes more than once. The closed walk is where you effectively there's some way in which you come back to the same vertex. Okay, so is it A to B, or is it A going through a series of nodes back to start point A? That's a closed walk. An open walk is where that's the A to B type of scenario. Now, we can have a walk that's just going in any direction. We can walk around in circles. We can walk in all sorts of directions. Okay, but a path is where you're not visiting vertices more than once. Okay, and we talked about that. So a walk can be any combination of nodes and vertices, visiting and traveling them as many times as you like, but a path is a little bit more, requires a certain amount of efficiency. You can't go through a vertex more than once. So a cycle, okay, is a path that is closed, i.e. you go back to your start, basically. And yes, I suppose you're visiting the start point when you get to it at the end. Yes, you visited more than once, start at the beginning, at the end, I get that. But basically, effectively, a vertex doesn't have to be visited more than once. Okay, so a cycle is a path that is closed. Now, I mentioned to you about a tree. So a tree is this sort of connectivity of vertices, but there are no cycles. Okay, it's not a loop. The idea of connecting around in a variety of different ways. Okay, so and you can see the idea of a tree, the branches coming out. Okay, and then a spanning tree is where where you're visiting all the vertices of a network. okay, with no cycles. And the key thing about the idea of the cycles is if you have a cycle, then it creates inefficiency. So going back to that example, okay, if I draw any other line, if I draw the line between Kilkenny and Callan, or the line between Kilkenny and Thomastown, or the line between Callan and Ballyhale, I create some sort of cycle, some sort of, it's not a loop, but the idea where you've got that. So if I draw a line through, hang on, let's get my pen, let's see if I get my pen to work. If I connect that up there, okay, you've got a situation where you've got effectively a cycle inside your graph there, okay. We don't want that in a spanning tree. Okay, likewise, if I connect up Callan to Ballyhale, it's unnecessary for the purposes of that idea of a spanning tree, because the idea here is that if I want to send something from Ballyhale, okay, to Callan, okay, you can just go via that journey. The cost doesn't matter. I'm just traveling that journey from Ballyhale to Callan. It might be, you know, a message being sent by an email, going through various different servers on a large internet network, and it takes milliseconds. So the cost actually isn't important, okay, but it will get from Ballyhale to Callan. Okay. So the idea of trying to create a situation where you do not have a cycle. We can have connected graphs, we can have disconnected graphs. Again, it should be fairly obvious. You can see in the diagram here, you've got clearly a situation where there's a disconnect. We've sort of like you've got two separate graphs that aren't connected together. Okay, so a connected graph is a situation where all the vertices are effectively connected together. There will be a path, a walk through all of those vertices. Disconnected one is where you can't complete a path or a walk through all the vertices because there's some disconnection that allows you not to be able to access some of the nodes from the other set of nodes. Okay, as it looks like a bit like two separate subgraphs. There is a thing that's called valency. Okay, and the idea of this is about how many edges are connected to a node. So very quickly, I'll go back to that slide in a second. If we looked at Kilkenny, for sake of argument, we can say that Kilkenny has got 1, 2, 3, 4 edges coming out of it. Okay, Gowran has 2, Thomastown has 3, Ballyhale has 2, Callan has 3, Kells have 2. So valency is the number of edges coming out of a vertex. It can also be referred to as its order or degree. So what's the order for Kilkenny? It has an order of 4, okay, or it has a degree of 4, or it has a valency of 4. Okay, if there was directed graph where an edge has a certain direction, you can talk about how many edges that are going into a vertex and how many coming out, and you sort of effectively have two numbers, one describing the ins and one describing the outs. Okay, so the degree or valence or order would have two numbers to go with it, paired up. So just very quickly again, there's a long summary there of the various different concepts. So a walk is a route through a graph, doesn't matter what's going on. A closed walk is one that ends and starts and ends at the same place. An open walk does not end at the same place it started. Now a path is very specifically, it's a walk where you're not visiting a node more than once. A cycle is a path where you start and end at the same place. We talked about connected and disconnected graphs, and we've talked about trees and spanning trees. Now, just going back to the example I had of, I think it was, I didn't look at the scenario of traveling all arcs exactly once. And there's probably a question in one of the exercises about this, but I'm going to go through it anyway. The most famous one of all is the Bridge of Königsberg. Okay, Königsberg doesn't exist anymore. I can't remember which town it's now called. Is it Kaliningrad? I can't remember. Anyway, and not all these bridges exist anymore. But there was a time, about 400 years ago, when there were these bridges across these sides of the banks of a river, and the river, the two rivers met together, and there was also a bit of an island before the river goes from right to left and goes off somewhere. I can't remember where. Look it up. Anyway, the idea was, okay, you've got these people out on a Sunday, and they're wearing their finest, and they want to be seen, but they don't want to be seen to be seen, i.e. they don't want to look like they're trying to parade and around, but they are trying to parade around and be seen. Okay, so how can they do it in the most effective way where they don't cross a bridge more than once? Okay, but still visit effectively all the go around the entire sort of network, I suppose, of banks and islands, but they don't want to look like they're doing it because they're having to travel a bridge more than once. So let's just turn this now. That as I've presented to you, it probably, oh God, how would I go about doing that? And this is where a graph can help to, and a graph or network can help you to simplify the problem. So what we'll do is we'll see the bridges as being arcs, edges, and we'll see the parts of the city being nodes. Okay, so all of a sudden we have that. We have 4 nodes, because we have the two banks, north and south, and we have the island, and then we have the other bit to the right hand side there where the rivers come together. It's another sort of island, I suppose. Getting rid of the map now. That's what it looks like now. That in of itself is a little bit excessive. I've tried to meet with where the bridges were, but let's just slim it down a little bit. Okay, so you can see that I can just sort of simplify it a little bit. Okay, so those two bridges that go from the island to the north side. Okay, I'm just trying to draw them equally. So there are your 7 bridges. 1, 2, 3, 4, 5, 6, 7 bridges. Okay, they are represented by the arcs, the edges, and you've got the 4 nodes which represent the 4 different parts of the city. And so the question was, could you travel around that network and be able to travel every arc exactly once? Okay, if you did a bridge, if you did an edge more than once, then you might be spotted. Oh, hang on, they're going around in a circle, and they're trying to be obvious they're parading around. So, can you travel this network, starting and ending where you like? Okay, but where you're traveling an edge exactly once. So that was the question that was posed in the Bridges of Königsberg problem. Okay, and I'll give you a little hint. You can use the idea of valencies to be able to. So I said to you that the clue to this question is looking at the valency of the various different nodes. That will help you solve the problem. Okay. If you can do it, how can you do it? Where do you start? Where do you end? If you can't, okay, well, how many of the bridges can you do? Okay, so I'll say that. Otherwise, second question will be, okay, if I said we don't have to do every single bridge, but do as many bridges as possible, but only do them exactly once, whichever ones you do travel. Okay, how much you do that. Okay, so I'll leave that with you, and there's a whole series of exercises that you can do. If you go to chapter 11 of your textbook, starting from page 198, there's a whole series of repeating the notes that I've gone through there, and there's exercise 11A, starting on page 200, and then there's more explanations about walks, paths, and cycles, And again, there's an exercise 11B on page 207. Okay, so you should be able to work your way through that. Okay, up as far as page 209. I rambled on for 40 minutes, I'm sorry, but there's plenty there. I'll upload the notes, the slideshows, so you have that if you want to print it off. Okay, any questions, let me know.